Hello everybody, I hope all of you are well. In this video, I'm going to discuss about soil aggregate stability. Soil is more than a mixture of sand, silt, and clay. It's a living structure that breathes, absorbs water, and nurtures life. One of the most powerful indicators of a healthy soil is aggregate stability, the ability of soil particles to stay bound together when exposed to rain, wind, or mechanical disturbance. Stable aggregates are like the bricks and mortars of the soil. They determine how air, water, and root move through the ground, how microbes thrive, and how much carbon the soil can store. In other words, aggregate stability is the backbone of soil physical quality. How can we define soil aggregate stability? Soil aggregates are clusters of particles bound by organic matter, microbial secretions, and fine roots. Their stability refers to how well they resist breakdown when wetted or disturbed. When aggregates are strong, rainfall infiltrates easily, erosion is minimized, and plant roots can expose freely. But when aggregates are weak, soil crusts form, water runs off, and valuable nutrients are lost. In scientific terms, aggregate stability is often quantified by mean weight diameter, that is MWD, the average size of stable aggregates that remain intact after weight saving. When mean weight diameter values indicate higher mean weight diameter values indicate better soil structure and resilience. So why aggregate stability matters? Let's talk about it. Aggregate stability affects nearly every soil process, from infiltration and aeration to carbon storage and microbial activity. Stable aggregates protect soil organic carbon from rapid decomposition by enclosing it within microenvironment or microaggregates that are less accessible to microbes. This protection mechanism helps build long-term soil carbon stocks, making aggregate a key driver of soil carbon sequestration. In agricultural systems, aggregate stability is the difference between productive, resilient soil and degraded, compacted land. Soils with poor aggregation suffer from crusting, compaction, and reduced water availability, problems that directly limit plant growth. Let me share the insights from long-term no-tillage and organic amendment research in Ohio. At the Ohio State University's long-term conservation agriculture and organic amendment plots established in 1997, scientists have been studying how no-tillage and organic amendments influence soil structure. I'm also working on that agricultural plot. After nearly 27 years of continuous management, the results are striking. Compost and many treated soil show the highest aggregate stability, reflected in larger mean weight diameter values around 1.8 to 2 mm at the surface layer, like 0 to 20 cm, compared to fallow or cover crop plots, which exhibit much lower stability. This improvement arises from enhanced soil organic carbon, biological binding agents, and reduced disturbance under no-tillage. Manure, with its readily decomposable organic matter, boosts microbial activity and root growth, leading to temporary binding effect. Compost, on the other hand, provides more recalcitrant organic matter that strengthens aggregates over time, resulting in long-term structural improvement. At deeper layers, like 20 to 40 centimeter depth of soil, aggregate stability also improves under compost and manure, though the effect is less pronounced due to reduced root activity and organic matter input. Let me talk about the science behind soil aggregation. Soil aggregation is derived by the interplay of organic carbon, clay mineral, and root exudates. and microbial polysaccharides. Microbes act as the engineer of aggregation, producing sticky substances like glomalin and polysaccharides that glue particles together. Roots further enforce these aggregates through physical entanglement and rhizodepositions. When tillage breaks the soil repeatedly, it disrupts these bonds, exposes organic matter to oxidation, and destroys microhabitats. Under no tillage, however, the structure remains intact, allowing microbial and fungal networks to stabilize the soil naturally. This structural resilience not only improves infiltration and water retention, but also enhances plant available water capacity and soil porosity, linking physical stability to hydraulic function. Let's talk about why aggregate stability is a climate solution. Improving soil structure isn't just an agronomic goal, it's a climate action. Each stable aggregate acts as a tiny carbon vault, protecting organic matter from decomposition and carbon dioxide loss. By improving aggregation through compost, manure, and conservation tillage, we can increase soil's carbon storage capacity while improving productivity. Stable aggregates also reduce erosion, preventing the loss of fertile topsoil and minimizing sediment transport into waterways. Thus, aggregate stability serves as a bridge between soil conservation, water quality, and climate mitigation. Let me share my research perspective. In my PhD study at the Ohio State University, I'm quantifying how long-term no-tillage and organic inputs influence aggregate stability, soil carbon, and water retention. By integrating field measurements, statistical modeling, and principal component analysis, I'm identifying how structural indicators like mean wet diameter, soil organic carbon, and bulk density collectively define the soil physical quality index. Preliminary results show that aggregate stability is strongly correlated with soil organic carbon, meaning that as soil carbon increases, structure becomes more resilient. This mechanistic link highlights how organic management not only feeds the soil but also engineers its physical integrity. Soil aggregate stability is more than a scientific metric. It's the foundation of sustainable agriculture. Healthy, stable soil aggregates mean better infiltration, stronger root systems, and greater resilience against drought and erosion. Every compost application, every year of no tillage, and every cover crop planted adds another layer of strength to the soil's architecture. By protecting aggregates, we protect the entire soil ecosystem and the future of farming itself. Because when we stay together, the earth stays alive. Thank you so much for watching this video.